Okay, Sean. So we had a 3-hour crash course on Brownian motion and stochastic differential equations. I hope you enjoyed it. But I don't know. So I actually decided to put in a couple homework assignments to clarify it. I mean, it's amazing what you can do with so little information. Basically, you have enough to actually have a lot of intuition about stochastic differential equations, even though you don't know the basic theory, which is why these solutions to these things exist. I mean, that's pretty deep. But if you just take that for granted, I believe it exists, and believe these martingale properties hold, then you can do a lot. And frankly, that's what all of us do. I mean, I did learn the construction of the Ito integral when I was a grad student, and I couldn't reconstruct it. I would have to spend some time, reviewing that. I just take it for granted now, so you can too. Some of you will learn about it in the math course, but most of you will not. It's still useful even if you don't know all the theory. So anyway, so here's another building block, and it's something that I every time I've taught this course, I think, should I really do this or not? But it's so fundamental. You've got to know what these things are. And in this lecture, we'll get to practice a lot of tools again. So it's useful just in terms of mastering the machinery. But this counting process is just a process that looks like this. It's 0 for a while, then it jumps up. It's 1 for a while, it jumps up to 2. It's the most boring looking thing you've ever seen in your life. So again, n of t, this process will be the number of events up to time t, which means like the number of jumps. And you can, given these increasing times, tau 1, tau 2 times tau 3, it's an infinite sum of indicator functions. All right, so basically I'm counting up the number of times that t is less than or equal to tau k. That's what this is saying. All right? So the case that people typically are concerned with is when these inter-event times are IID. What do you think I'll assume about them? No martingales, no.
That they're conditional mean 0, like.
Oh no! Oh God, no! These are interval times. They could be positive. Yeah. No, they're not gonna have mean 0.
The increment will be 0.
No. They're positive, right? No, they're positive random variables, so the mean is positive. Yeah. No, they'll have positive means, but they're going to be IID. It's a typical assumption you'd make. Yeah, so if these are IID, then it's called a renewal process. Okay, so renewal processes, you'll find them all over the place. And typically, you'll find this more in the operations research side of the world. So in basically, this could model arrivals of customers to a bank or arrivals of packets in a communication system, something like that. But mainly you need to know what these are about, and in studying this, we get to practice the machinery. I guess that's the main thing. So the very, very special case which I'm going to focus on is a Poisson process. And when I learned about them, I was given one definition, and I see that Bruce Hayek has a different definition. They're both equivalent. I'm going to use his definition. So this is all out of chapter 4. All of this is chapter 4 of Hayek. And I'm following his notes really, really carefully. So if things aren't clear, don't worry about taking very careful notes. This should look familiar to you. So you notice I'm using the same notation I use for Brownian motion. I'm letting zk be the difference of the process at different time, time indices. And these are independent. Are they Gaussian? No way. Because this is the number, this represents the number of events that occurred in this interval of length tk minus 1. And they have a Poisson distribution. And the notation so a Poisson process, I should say, with great lambda. And so, what do we know about Poisson processes? I don't know. The mean of a Poisson process is what? Anybody remember? It's almost that. So it's 1 over what you said. So it turns out the mean of a Poisson random variable, if you work it out, you can actually compute it pretty easily. You just sum over n times the probability of zk equals n. You can see it's not that hard because n over n vectorial, not too difficult. So it turns out to be beta. And that's actually equal to the variance as well. And that might, look a little bit, something's going to look familiar to you. So if you look at what's the mean of n of t. And beta, sorry. Beta, I'll just write it down again. So what's the mean of n of t given all that? So lambda in there. This is just one giant increment, right? That's just a z with taking t to 0. So that's lambda t. And the variance same thing. It's just going to be the same quantity. And I've got independent increments. I've got this nice mean behavior. From this, I can say that if I define m of t to be n of t minus its mean, then you can say it. Then I get my martingale. Okay, because it has independent increments, you can check, and you've got a zero mean independent increment process. It's got to be a martingale. So just check the definitions. A zero mean martingale. So you've got this zero mean martingale with independent increments, and its variance grows just like t. It looks like its second order statistics are just like Brownian motion. You'd say, if I was just giving you that, you'd say, oh, it's a Brownian motion. But the sample paths, if I subtract off lambda, it's going to be some funky diagonal thing. It doesn't look anything like Brownian motion. But there is a stochastic calculus for this. So you could derive all the stochastic differential equations we talked about before using this instead of Brownian motion. So stochastic calculus exists. You might have some system driven by a Poisson process, and you have some output coming out, and you could keep going. We won't do it, don't worry. But you could develop all of that machinery. All right. What else do I want to say? Okay. All right, anyway, so the program is just to understand a process, because this is not a very intuitive thing, right? Understand what a Poisson process is, a little more deeply. And again, I think my only motivation is you need to know what this is, and we need to practice some of the probabilistic math. All right? And so this is a bit of a detour in a way. All right, so what can I kill? Yeah. I don't care about that. So here's a crazy result. Okay, this is the following are equivalent. So first, we have this, this very complicated definition, independent increments, and a Poisson distribution for each increment. The next one is going to be about these delta guys. And anybody, some of you know what this is? Well, they're IID, so a Poisson process is a renewal process. And they have a distribution which is So the means of the delta is a 1 over lambda. So if lambda is very, very big, then the mean is very, very small. So you have a lot of events per second. All right? That's why there's inverse relationship. Right? You know, I've got this, the lambda here is the, yeah, anyway, right here. The mean of the increment grows with lambda because you have a lot more events if the mean of delta is small. Clear? Yep.
ZK, like delta?
No. These are, yeah, it's really hard with the notation. What you see is whenever I write little tk, these are just numbers I picked out of a hat. Okay? And I'm using these tau k's for the random variables, the event times. Okay? So again, these are just arbitrary times. Those aren't taus. If that was tau k minus 1, you're right, that would be delta k. Yeah. Sorry about the notation. It's just.
So it seems to me like ZK is always 1.
No. These are for any numbers. Yeah. So I could take, oh, look, a blue pen. You know, this could be T1 and T2 and T3 and T4. You know, so those are numbers I just throw down there. They, you know, they're not, yeah. Okay, so that's really nice. So this is a much simpler description of a Poisson process. These are equivalent, and that's how it was defined to me. I mean, a Poisson process definition, it's a renewable process with exponential increments. And C, this is what's fun. Take a deep breath. So first, no surprise. I just take one giant increment, you know, and I say that, you know, n tau is like an increment, n tau minus 0. It's Poisson with parameter lambda tau. That's no big deal. But here's a weird, instead of talking about all the increments, here's another way of thinking about it. So I'm going to condition, for any n, I could condition on the number of events being n, and I want to think about how those times were distributed, you know. And the idea is that given, I pick a time tau, And in this case, n equals 3. And I want to ask, how are those guys distributed in this line? And it turns out they're sort of uniformly at random. It's so hard to see this. So I'm saying this in words, and then I'm going to be more precise. So basically, I say conditional on n of tau being n, say n is 25. I draw a uniform random variable from 0 to tau, do it again, do it again, do it again, do it 25 times, n equals 25. And then I look at them and I call the first one tau 1, the next one tau 2, the next one tau 3. So you're basically just slapping down 25 random variables independently. The way you make that precise is to write down the density. So this procedure of drawing n ID random variables defines a density. It turns out this is the same as saying that this conditional density of the position of the time points, given that's not n equals, yeah, n equals n, that's right, n equals n, is a constant on this strange, this strange region, this wedge. And what's the constant? Well, anyone can do this. It turns out that if you integrate this wedge, the volume of this wedge is tau to the n over n factorial if you do the calculus. And so this is just the normalizing factor to make sure the density does integrate to 1. All right? Okay, so we've got a restricted domain. We've got tau is fixed, it's not random, it's just a number that we chose. N is just some number we chose. This is true for any tau in n. And if you integrate this, if you look at the volume of this region in Rn, it's tau to the n divided by n factorial. So this is just a normalizing constant. So we're going to prove this. I've done it before and we've all survived, so don't be scared. It turns out that proving A implies B is tedious, but not bad at all. B implies C, you can imagine, takes more work. It's more difficult. And then C implies A is just the same sort of step. So I'll skip that. But it's I think it's worth doing. All right, and let's do it. Okay, wait, that's the order again. We prove that A implies B implies C and then implies A, and that means they're all equivalent. Right. And I'll have to rewrite this. Oh, that was a big mistake. I erased the definition of a Poisson, a random variable. Should have kept it there. So somebody will have to remind me. All right. So A implies B. So what we have to do is, I mean, you can see it's a lot of information. I'm starting off with this Poisson process with one definition, and somehow I have to go and say that these building blocks are ID and with an exponential distribution. So how do you do that? You have to look at a probability of a certain event. Basically, give me epsilon greater than 0. And give me also a bunch of times. And I need to take a probability of an event given that data, and I'll explain it as I go along. So I drop down T1, T2, T3. Again, Neil, these aren't random variables. These are numbers you gave me. So, this is E, this is pi, this is pi squared. I don't know, they're just numbers, okay? And then I've got, I shift over a little bit. And just think about what I'm doing. Just don't take notes. I mean, think of what is Professor Mine doing? Remember my goal. I'm starting off with this strange thing about increments. So I know all about increments of this counting process, and from that I want to tell you something about the jump times, the inter-event times, and so I want to look at the probability essentially that a jump occurred in this interval, and then one occurred in this interval, and so forth. So the first jump was here, the next one was in here, the next one was in here, and so basically, I'll sketch that out. So this is just symbolically. I want to know the probability of this sort of event. So let's write that down. So when I compute the probability of this blue thing, I mean that my first jump occurred in this interval, and the next jump occurred in this interval, and so forth. And I made it open on the left and closed on the right. No big deal. I mean, it's nothing. So why would I do that? I'm trying to compute a conditional density. What I really want to get at is that I want to say that if I take this, here's the goal. Well, a fact, first of all. So you'd all agree with that. If I want the joint density of a random vector, what do? I look at the probability that of each of the random variables being, tau 1 is in the first interval, tau 2 is in the next, tau 3 is the next, and so forth. I look at the joint probability of that event of being in a cube, So there's a probability of being in a cube, and I divide by the volume of the cube. So this is the probability of being in a cube, and that's the volume of the cube. All right, so that's something you all should, keep in your memory banks. So you can see why I want to do this. I want to sort of practice this basic stuff, So anyway, that's the fact, and that's the thing we want to compute, because in order to prove B, we need this joint density, and we need to show it corresponds to the taus being IID and having an exponential distribution, right?
So that function right there is epsilon to the n times the nth order EMF. So that's how you define an nth order EMF.
Yeah, that's the density for the n-dimensional, the random vector. Yeah, tau 1 to n, tau n. Yeah.
Why is it epsilon to the n?
Well, because that's the volume of the cube.
What is it if you bring it up to the top?
Oh, no, I've got the density over here. So p epsilon, Yeah, so this probability is going to be like epsilon to the n, because we look at the probability of being in a cube, n-dimensional cube, and the volume of that cube is epsilon to the n. Yeah. All right, and so now we get to practice our magic with disjoint intervals. We can use we're assuming A, so we can use the fact that the increments are independent and identically distributed. And we've defined the event of interest in such a way that it's really simple to compute the probability. All right? It's a little tedious, but let's do it. All right. So again, it's written in terms of the tau i's, but we know nothing about the tau i's given A. We're trying to prove something about the tau i's. So we've got to write this event in terms of n instead of tau. All right? Is that clear? I mean, it is clear, right? The definition of Poisson process says nothing about the tau i's, the inter jump times. And we're trying to deduce something about the inter jump times. Clear? All right, so we've got to translate this. So how would you express this event in terms of n of t? Well, at first it says that, that this is 0. And it also says that the difference here between the n's is 1. All right. So here we have 1. And then we have to keep going. We have to see nothing happened here. And then we have to say there was one jump at time, t2. We're going to be able to work this out. And then we go off to the end. There's going to be something similar to this. So this corresponds to that last quiet stretch, something like from here to here. And then find the last guy is yes. All right. Yes.
Is the probability of the union of all these events?
No. Yeah, it's only a union. So this is, when I write the probability of something for 1 less than or equal to n, I mean the probability of the union. It's the same thing. Okay? So that's just notation people use in probability. It says, this comma or such that always means a union. Yeah. Not union, intersection, and, not or, and. Sorry, not union. Excuse me, God. All right, so I want this to be true for each I. So intersection. And so the same thing here. This is intersection. This and this and this. So commas mean and. That's what I mean. Yeah, it's too bad we don't use ampersands. That would be nicer. Okay, so now you see we've got independent increments, because this first guy's an increment. I'm looking, I can subtract off n of 0 if you want, because n of 0 equals 0. And so that's an increment, and the disjoint time intervals, so it's a product of probabilities. How far? This is so hard to read. I should be careful. I've got all my friends here. Keep going. I'll put in ... Done. Okay. So we've got that. Yes. Oh, no, the independent increment. So I'm trying to prove A equals B, and there were two properties of the Poisson process. One was the independent increments, and that's what I used here. Okay. So I've got these are increments, and they're disjoint time. I'm looking at these disjoint time intervals, and so I get the product of the expectation, a product of the probabilities. All right. So now, but I haven't used the Poisson property, the fact that there's a Poisson distribution. So I've got to work out what these guys are. And so what's the probability that n of tk minus n of tk minus epsilon equals 1? This is what I was saying. I wish I hadn't erased that definition. So it's, I've got the parameter is, I've got this is Poisson with parameter which is the length of the interval, which is epsilon, times lambda. So it is, what is it again? Somebody tell me. It's the That's right, isn't it? Yeah. Yeah. Oh boy, so okay, so we've got this this horrific looking product, but all the terms are very easy to work out because the probability that one of these guys is 1, because this guy is just a Poisson or an invariable